Hello, everyone. So, in the last episode, we were looking into the history of computers. Well, at least we skimmed over it to some extent to get some context for why we are building a historic style computer and, yeah, what the purpose of it all is. However, today we'll look into what will actually make our historic computer tick: logic gates, and especially how we will implement them in hardware, since, as you remember, we won't use any like 74LS chips or whatever. We'll do everything in discrete components, just like people used to do. So, in particular, our computer will use what's called Diode-Transistor-Logic, or DTL. Well, it's gonna be a little bit beefed up DTL for sure, so it's not what people used back in the days. There will be some improvements, especially to the output stages and buffers and everything there. But in principle, it's still the same stuff that was used in the IBM 1401 back in 1959. Yeah, but to understand everything, we will have to dive a bit into the older resistor-transistor-logic, or RTL, before we can graduate to our DTL logic that we are going to be using. So let's do just that. So first, just a quick overview of our logic gates. There are three basic logic gates, and yeah, that's what we will talk about here really quick, since we will need those to build our computer. First, we have the AND gate. And as the name says, the AND gate will have a 0 at the output whenever the outputs are not equal. But if both outputs, so 1 and 2, is equal, they will output a 1. Obviously, there's the NAND gate, or sometimes called NAN. And yeah, this is basically just the reverse. It's gonna output a 1 or true every time the outputs are not equal, and a 0 when the outputs are equal. And the operator, when we write down formulas for later, for an AND gate, will be a multiplication symbol. Okay, so that's basically the AND gate. Let's go to the next one, the OR gate. And as the name says here, the OR gate will output a 1 when either input 1 or input 2 is 1. That also says input 1 or input 2 for here. Basically, when both are 1, the output is 1, 2. Also here, the corresponding negated output gate is the NOR gate, which will be 1 only if both inputs are 0, and 0 if either input has a 1. The operator for that is a plus symbol. Just like addition, and we'll see later that all the mathematical operations will work the same as with regular numbers too. So multiplication before addition and stuff like that will hold true for logic stuff as well. And last but not least, we have the buffer or not. And yeah, basically they just repeat what is in the input or negate what is on the input respectively. You might find some uses for NOT gate, but buffer, why would we just want to repeat something? Yeah, it is actually interesting how useful a buffer is, and we will see that later once we get to the actual implementation of stuff. And yeah, for that, the operator is either an exclamation mark before the value or just like an overline over it. Okay, those are the three basic logic gates. However, there is a fourth one which is sometimes considered to be basic. However, it is only basic because the functionality of it is so useful. It is actually made up of multiple single gates, as the implementation of that as a basic gate is, well, I wouldn't say impossible, but I haven't seen any direct implementation that doesn't use ands and ors. So let's just have a look at the exclusive OR gate really quick. So the exclusive OR gate is very similar to an OR gate. However, you can see here, if both inputs of the exclusive OR gate are 1, the output will be 0. So the output will only be 1 if either input 1 or input 2 is 1. Not if both and not if none. The operator for that is like a little addition sign in a big circle. And let's just see really quick how that is implemented. So the easiest implementation is you have an NAND, an OR, and an AND gate here, which will basically replicate that functionality. A and not B, or not A and B. And you might see that we don't really replicate that function down here. And that is simply because you can simplify that into what you see up here with the NAND, the OR, and the AND. You can basically factor out stuff and put it together so that it represents this formula that is displayed up here. However, a more useful implementation of that is down here with 4 NAND gates, which is simply due to the fact that NAND gates are easier to build than OR gates or AND gates. So this is most likely what we are going to be using in our hardware when we want to implement an exclusive OR gate. And just to give you a little taste what it can do, basically what you see here in XOR gate is almost like a simple addition circuit, almost. So as you might know, or might see, this is going to be used extensively in our arithmetic logic unit for addition, or like even for controlled inversion and negation of stuff. So very useful. Okay, so now that is the theory about how logic gate works. So let's see how it is implemented. Let's start with something easy. Resistor-Transistor-Logic. This was actually one of the earliest implementation of logic gates, or of electronic logic gates to be exact. And it was extensively used in the Apollo guidance computer. So that stuff actually flew to the moon. Pretty amazing for how simple it is. And yeah, let's just have a look at it. So our gates here are the NOT gate, the NAND gate, and the NOR gate. And as you see, everything is negated just because a negated gate is easier to implement in hardware. So how does that work? Let's have a look at it here with our NOT gate for now. So if we input 0 volts, which is basically a logic low on the input here, no current is flowing through the base here because current can flow from 0 volt to 0 volt. It just doesn't. There's no gradient in there, which means that that transistor is actually not conducting any electricity between its collector and its emitter down here, which means we are not dropping any voltage over that resistor up there. And that means that our output here is 5 volt logic high. So as you see, we put in logic low and get out logic high. So let's have a look what happens when we put 5 volts on the input here, which is a logic high. In that case, current will flow here over our base current limiting resistor into the base of the transistor and down to ground. And that means that our transistor here will start conducting between its collector and emitter, because that's how a transistor works. If current flows into the base, the current that flows between collector and emitter is basically just an amplified version of the base current. And that also plays into how we size our circuits and stuff like that, because let's say our transistor has like an amplification of, let's say, 100. So we basically may have to make sure that the current we put in is the current that is needed to get a full voltage drop of our load resistor here once our transistor is basically conducting, and with a nice safety margin on top. So usually it's like double what is needed, and then it'll just work. Let's just set load current will flow. All of our operating voltage will drop over our load resistor here, and we have 0 volt on the output. So logic high in, logic low out. And yes, you might imagine it works similar for our NAND gate, only that we have 2 transistors in series, which means we can only pull our output to ground here once both inputs are actually high and conducting current through the bases of those transistors. Same with the NOR gate, only that you can see here the transistors are in parallel, meaning that current will flow if either of those is conducting. So if either or both inputs here are at high level, which will output a low level on the output. Okay, so that was Resistor-Transistor-Logic. So let's look at what we are gonna use at Diode-Transistor-Logic. So first, to see how the actual logic works in that, let's look at the regular diode logic AND gate here. Notice there is no transistor involved, so this is just a regular AND diode logic gate, which we also call a wired AND gate because no transistors are involved and it's basically just wired together like that. And yeah, here, as you can see, our VCC input has no way to go if both of our inputs are at high level. However, as soon as one of our inputs is at low level, current can flow through it, and that will basically flow out through the diode and pull our output low. So this is an AND gate, meaning our output will only be 1 if both of our inputs are 1. As you might also see here, and see what problem we are gonna solve with it in regards to resistor-transistor logic we looked at before. Let's just go back to that really quick. As you can see here, our output is driven through that load resistor here. So any output that is after that will have its current have to go through that load transistor, meaning that since our transistors need a certain amount of current to switch, we need to first have our load resistor be fairly small so that we get a lot of current on the output here, which will increase the power consumption of our gate. But also we are limited in how many outputs we can connect, or inputs we can connect to this output here. So in our diode logic, we don't really have that problem since everything will basically go to ground. So the only current flowing in diode logic will basically flow through the transistor, which has a pretty low impedance, down to ground. There's no current flowing from the high level here. So just to illustrate that, both inputs are 5 volt. The output is 5 volt. One input is 0 volt. Current flows through here, through our transistor in our previous stage, and drops through the load resistance here, and our output will be 0.7 volts in case, well, it's just a diode drop, so it's not necessarily 0.7 volt, but for all intents and purposes, it is. And that you might see is a problem here too, because we'll always have that diode voltage drop here on the output, and there's no way to get rid of it. And if you cascade diodes one after another here, at a certain point, you will be at a point where you don't have any voltage difference anymore. Nothing can flow through the diodes. So that's a problem. How do we fix that? Well, we can fix that with transistors. So this is our first diode transistor logic gates. Yeah, very simple NAND gate. And as you see, the only thing it does is combining our input with a diode network here, which we just learned will only let current flow through the output transistor of the previous stage to ground. And so our load resistor here doesn't really matter that much. But we connected a resistor-transistor-logic gate behind it, which means, yeah, we do get that big transistor output capacity, and we lose the diode voltage drop here. So this will always be at pretty much 0 volt on the output, no matter how many gates we cascade after each other. Yeah, so this circuit has some issues. As you might notice here, if both of our inputs are high and we were just coming from a low state here and we have to switch our transistor over, our charges that are going to be in the base here have nowhere to go. They can't flow reverse bias through those diodes, and they have a pretty big resistor here. And so yeah, that our transistor will take a long time to switch out of saturation and into non-conductive mode. Yeah, that's a problem. To fix that, what we can do is to add 2 diodes here. And those 2 diodes here will first increase our noise tolerance, since we basically lose that bias that we get from the diode input network over the other diodes back here. And yeah, it doesn't fix really our switching issue. However, we can fix that by tying either ground or negative voltage via resistor to the base here. And that gives our charges here on our base junction a path to discharge. So this will basically increase our, or improve our switching time, not increase it, but actually decrease it by quite a bit. However, we are not quite there yet. We can do one better. So let's have a look at our actual circuit that we are going to be using in our computer. So here it is. Looks intimidating maybe, but let me assure you it's not that bad. So first let's just go through it from left to right. On our input here on the power rail, we have a bypass cap, and that is basically just to remove any ripple that we might get from our switching action from the supply line, which might interfere with other parts of our computer. It's probably not necessary since our computer won't be that fast, but it doesn't hurt to have it, and who knows? Those things are super cheap and they might prevent our computer from malfunctioning. Then here you see our input diodes, and basically you see input 1 and extension. The nice thing about Diode-Transistor-Logic is that if we want to have, let's say, an 8 input gate or 9 input gate, we can do that by just adding a couple diodes in parallel here on the input. And yeah, we will have an 8 or 9 input gate easily by just adding diodes to this circuit. Then over here, our next stage is a transistor. And yeah, you can see here our transistor is in an emitter follower configuration, which means the voltage on the output will be the same as the voltage on the input, pretty much. However, it will allow us to supply a lot more current to the base of the switching transistor that is coming up. Also, here we have that pull-up resistor to our diode network on the base, and this does not only pull up our diodes, it will also help discharge the base here when we are switching, improving responsiveness of our transistor. Then here we'll have the BIOS diode, which is again for noise reduction, so it increases the distance between high and low thresholds. And as we saw before, here is our discharge resistor, which in our computer will go either to ground or to -5 volts. just an FYI here, you need to be a little bit careful here because the base emitter junction usually has a fairly low breakdown voltage. In case of the transistor we are using, the 2N3904, and we'll go into that in the next episode as to why we are using that transistor particularly, has a base emitter breakdown voltage of 6 volts. So if we exceed that voltage here, then yeah, nothing good happens and our transistor might die because it's not built for actually having current flow reverse over our base emitter diode junction here. And yeah, as you see, this is basically our switch, which will generate an AND output. However, you see that little BAT43 Schottky diode here on the base coming to our collector. And that is what is called a Baker clamp. So what this is doing is basically it is pulling up here our input a little bit so that it's just the Schottky diode forward voltage below our input, which means our transistor here never really goes into full saturation. And that is good, since in that case, when we switch it off, it doesn't have that many charges to get rid of, and it'll switch off very much faster than without it. Well, not that much, but it's quite significant and noticeable. The problem right now is those diodes are super expensive, especially if you want to have a leaded package. Most things nowadays go over surface mounted packages. However, leaded packages are still available, and we don't really want to use surface mounted packages here since it's not historically accurate. And well, that's just where I draw the line. I know that those transistors here weren't available back in the days. Maybe not even the TO92 package, but yeah, I just don't want to use surface mounted devices. It's just where I draw the line. You might be different, so who knows? If I ever make the kit for that computer available, I might just put an SMD pad here for that diode if you want to use an SMD diode. Up to you. If not, you can leave it off and, well, reduce the performance of the computer just a tad bit. We'll see. And yeah, out here, how do we make an AND out of an AND? Well, we'll just invert the output with a little output inverter stage here. And as you notice, it's not like, for example, in DTL Logic, a push-pull output stage here. It's just a fairly large collector, load resistor, and our transistor, since, if you remember, we don't really use that current that goes from VCC. We only use the current sinking capability due to the diode magic that is going on our input. Okay, and that's pretty much it. Just for completeness, let's look here again on the AND gate, the OR gate, which is, as you see, two resistors, transistors in parallel with basically a diode input, just like our AND gate was, so that we don't have the problem with sourcing current through our load resistors. Works the same as in our Resistor-Transistor-Logic, just with the current sinking capabilities through our transistor on the input. Okay, that's it for this episode. Next time we will look into actually building those gates on a breadboard and playing with them a little bit, see what is faster and why we use the 3904 transistor instead of more commonly used BC337 or 2N2222 or whatever you're using. So yeah, don't forget to subscribe if you like that, and well, also like this video. And yeah, have a good one, everybody, and I will see you in the next episode.